Long before humanity built telescopes or launched spacecraft, the sun appeared constant and unchanging. Rising every morning with dependable precision, it became the foundation of life on Earth and the center of our solar system. Yet modern science has revealed that our star is anything but quiet. Beneath its brilliant surface lies a turbulent ocean of superheated plasma, constantly releasing streams of charged particles into space. This continuous outflow is known as the solar wind. Traveling at hundreds of kilometers per second, it carries magnetic fields throughout the solar system, shaping planetary magnetospheres, creating brilliant auroras and forming the enormous protective bubble known as the heliosphere. Every planet, asteroid and comet moving through our cosmic neighborhood interacts with this invisible river of energy. Normally, the solar wind behaves in ways that scientists understand remarkably well. Its speed changes with solar activity, its direction follows magnetic field lines, and its behavior can usually be explained using established models of plasma physics. But every so often, observations reveal something unexpected, an anomaly that challenges existing theories and demands closer investigation. One such mystery began when astronomers identified a rare visitor from interstellar space. Unlike ordinary comets that originated within our own solar system, this object arrived from another stellar system entirely. It became only the third confirmed interstellar object ever detected passing through our cosmic neighborhood, following the discoveries of Oumuamua in 2017 and Borisov in 2019. Naturally, telescopes around the world turned their attention toward this extraordinary traveler. Scientists wanted to determine its size, composition, rotation, and trajectory. Every interstellar object carries valuable information about the distant planetary system where it formed, offering a rare opportunity to study material that originated around another star. As observations accumulated, researchers noticed that this visitor displayed several unusual characteristics. Its brightness changed over time, and astronomers carefully monitored those variations to determine whether they resulted from rotation, changing geometry, or activity near its surface. Such behavior is not uncommon among small bodies in space, but understanding the exact cause requires detailed analysis using multiple telescopes and instruments. Among those observatories was the James Webb Space Telescope. With its powerful infrared instruments, Webb can detect subtle thermal signatures and analyze the chemical composition of distant objects with remarkable sensitivity. Every new observation added another layer of information, helping researchers reconstruct the object's physical properties. Meanwhile, spacecraft studying the Sun continued monitoring the solar wind. NASA's Parker Solar Probe traveled closer to the Sun than any spacecraft in history, directly sampling the outer atmosphere known as the corona. At the same time, the solar orbiter provided complementary observations from a different position in space, allowing scientists to compare measurements across enormous distances. Together, these missions have transformed our understanding of how the Sun interacts with the rest of the solar system. Occasionally, researchers identify unusual patterns within the solar wind, temporary distortions caused by magnetic activity, coronal mass ejections, or complex interactions between streams of charged particles. Understanding these events requires comparing data from multiple spacecraft collected over long periods. When different observatories detect similar features, scientists begin testing numerous possible explanations. Could the changes result from solar magnetic loops? Were they produced by rapidly evolving plasma structures? Or might they simply reflect the natural complexity of our dynamic star? This careful process is central to modern astronomy. Rather than accepting extraordinary conclusions immediately, researchers compare observations, build computer simulations, and eliminate explanations that fail to match the evidence. Only after exhaustive testing do new scientific ideas begin to emerge. In the case of this interstellar visitor, many questions remain unanswered. How did it form? What materials compose its surface? How long has it traveled through interstellar space? And what can it teach us about planetary systems beyond our own? Each new observation brings us a little closer to those answers. The arrival of a visitor from another star reminds us that our solar system is not isolated. It exists within a galaxy where material constantly moves between stellar systems over millions and billions of years. Sometimes, the greatest discoveries are not the answers we expect, but the questions that encourage us to keep exploring. As scientists continued studying the interstellar visitor, one thing became increasingly clear. The object was extraordinary simply because it had traveled between stars. Every measurement represented a rare opportunity to examine material that formed around a completely different sun, carrying chemical clues from a distant planetary system. But extraordinary discoveries require extraordinary evidence, and researchers remained careful not to confuse mystery with certainty. The James Webb Space Telescope continued collecting infrared observations, allowing astronomers to estimate the object's temperature, composition, and surface behavior. By analyzing how it reflected and emitted light, scientists hoped to determine whether it was rich in ice, rock, or complex carbon-based compounds. At the same time, spacecraft monitoring the sun recorded the ever-changing behavior of the solar wind. Streams of charged particles constantly interact with magnetic fields, creating waves, turbulence, and shifting plasma structures throughout the inner solar system. These environments are incredibly complex, and even small changes in solar activity can produce effects that challenge existing models. Because of this complexity, researchers tested every observation against known physical processes before proposing new explanations. Computer simulations recreated the object's trajectory, its rotation, and the conditions surrounding the sun during each observation. Scientists compared thousands of possible scenarios, searching for combinations that matched the available data. Some models suggested interactions with charged particles, while others explored how the object's shape and composition might influence the light reaching Earth's telescopes. This careful approach reflects how modern science works. Rather than beginning with dramatic conclusions, astronomers start with ordinary explanations and gradually eliminate those that fail to match the evidence. Only after repeated observations from independent instruments can researchers begin considering more unusual possibilities. Even today, interstellar objects remain one of astronomy's newest fields of research. Only a handful have ever been detected, meaning scientists are still learning what normal behavior actually looks like. Every newly discovered visitor expands that understanding, improving future models and helping researchers recognize patterns that would have gone unnoticed only a few years ago. The arrival of an object from another stellar system also raises fascinating questions about our galaxy. Planetary systems are not isolated islands. During their formation, gravitational interactions can eject enormous numbers of rocks, ice-rich bodies, and debris into interstellar space. Over millions or billions of years, those fragments wander through the Milky Way, occasionally passing close to another star. That means our solar system has likely been visited by countless interstellar travelers throughout its history. Most passed unnoticed long before humans developed telescopes capable of detecting them. Today, however, advanced observatories are beginning to reveal these rare visitors with increasing frequency, transforming them from theoretical predictions into observable scientific discoveries. Future missions promise even greater advances. The Vera C. Rubin Observatory, the James Webb Space Telescope, and upcoming ground-based observatories will dramatically increase our ability to discover and monitor faint interstellar objects. Instead of studying only one or two examples, astronomers may eventually build an entire catalog of visitors from distant planetary systems. Each new discovery will improve our understanding of how stars form planets, how planetary systems evolve, and how material travels across the galaxy. Perhaps the greatest lesson from these objects is not that they answer every mystery, but that they connect us to places we may never physically visit. A small fragment of rock or ice, formed around another star billions of years ago, can cross unimaginable distances before briefly entering our solar system and revealing part of its history. That journey reminds us that the Milky Way is far more interconnected than it first appears. Every star contributes material to the galaxy. Every planetary system exchanges fragments with interstellar space. Across billions of years, those ancient travelers quietly cross the darkness between stars, carrying with them the history of worlds far beyond our own.